Okay, so number 14 says, a 75 kilogram petty thief, okay,
75 kilos?
petty thief, yep, wants to escape
Oh, I know this.
from a third-story window. Don't say anything in advance, Jake. From a third-story window, okay? He's going to do the standard movie thing. He's going to tie sheets together to make a rope to climb down the wall. But he knows something because he studied his physics. And he knows about knots and material strength of sheets. I don't know why. His, probably Boy Scouts, yes. His makeshift rope can only withstand a mass of 58 kilograms. How can he still use the rope to escape? So he has a mass of 75 kilograms. And the fact is, if you hang a mass of 58 kilograms from the end of these sheets tied together, they'll break. And he doesn't want to fall 3 stories. Physics suggests he can still use this makeshift rope to escape.
You have to provide some upwards force, though.
I don't think you can add upward force to a rope unless you've got a way to staple it or a different material. Jake?
Double up the rope.
Then he won't reach the ground. He's got I should have put that in there. He's got exactly enough room to reach the ground, to where he could drop safely. But doubling up the rope would work. And then he'd be hanging 1.5 stories off the ground. And he doesn't want to do that.
Well,
Still
he can't survive that much, right?
You can survive a 3-story drop if you're lucky. But he wants to get all the way down. And he can do it. He absolutely
can't
can
you
do
survive
it.
a 1.5 story jump?
Sure. People have survived a lot more. But he doesn't want to take that chance. Yes, sir.
Go down 1 story, take the rope with you.
And reattach it somewhere? It's not going to have time to stop. They don't put ledges on these things. There's no place to stop and untie it. Plus, you'd have to have a way to unhook it.
Walk down the escape ladder?
Oh, yeah, that'd be candy.
Couldn't you make a parachute and just parachute out?
No. Air resistance will not kick in that little time, and it's not enough surface area, and it probably weighs too much. They don't usually make sheets out of the light enough, strong enough material to catch the air of the parachute.
You know, he could earn like
The mass of the parachute becomes a factor, in other words.
and just teleport.
And it's then-
No.
Teleport. Okay, we've gone to teleportation. It's time to give you guys a hint. All right, the 2 numbers I've given you, 58 kilograms and 75 kilograms, are they masses or weights?
They are massive.
They're masses.
So
Okay,
you gotta figure out the acceleration. What?
bingo. Here's my first Here's my first step to the answer.
That's what I was sort of trying to get at with the upwards force.
I thought you might be, but a 58 kilogram mass causes how many newtons of tension on the sheet? If you hung 58 kilograms from the end of the sheet, how many newtons of tension would that be? How do we find that? You have to give me the answer.
With the gravity.
The gravity, multiply that. Causes 58 kilograms times 9.80 meters per second squared, which equals how much? Just under 580, I hope.
568.4.
568.4 newtons. Okay. There's no such thing as tension without gravity. If you're in outer space, there's no tension. You can tie 58 kilograms to the end of these sheets, and it'll all just float there in outer space, weightless, but not massless. Still would have resistance to your efforts to push it. You need gravity to discuss tension. So this thing, this system of sheets he's made, can handle 568.4 newtons. That's what you have to think about when you think it'll snap if you hang the 58 kilogram weight at the end. Okay, it can handle 568.4 newtons. How can a 75 kilogram man cause less than his weight in newtons? Yes, sir.
Fly down.
Slide down's the right idea. The slide down is the right idea. Okay.
Wait, could he go part way and then let go?
Yes, but accelerate's the right idea, slide down is the right idea. Let's take a look at this. 568.4 newtons equals 75 kilograms times what acceleration? This is a calculator question. I'm not expecting you to do this one in your heads. Looking at me like you expect me to. Don't forget the dimensional analysis. If you get stuck, a newton is a kilogram times a meter per second squared. Divided by
7.57 meters per second squared.
7.57 meters per second squared. Okay, so it's obvious. He has to get himself to a planet with less gravity, where gravity is only this acceleration, right?
Oh yeah, just hijack it. Just hijack it.
Yeah, he doesn't have to take the whole building to another planet. No, he doesn't have to do that. What he has to do is make sure he is going down the rope in such a way that the rope only feels this much acceleration in terms of tension. Okay, he wants to simulate this. How can he do that? Well, if his weight would cause an upward tension on the rope of his mass times gravity, he needs to take his mass and accelerate it downward until this vector is only 7.57 meters per second squared. How fast does he need to be going down that rope? With what acceleration, I should say, not how fast, that implies velocity. So with what acceleration does he need to go down those sheets so that they don't snap?
2.23.
Where did you get that?
I did 9.8 minus 7.57.
Awesome. Okay, so I'll redraw this a little bigger. If he just hangs from the rope, it'll be his mass times 9.0 meters per second.
9.8.
9.80. And the only upward tension the rope can handle is his mass of 75 kilograms times 7.57 meters per second. Right?
Right.
So what he has to do is make sure that he is accelerating downward with the difference, which is, what did you say, Tyler?
2.23.
2.23 meters per second squared. So as long as he goes down that rope with an acceleration of 2.23 meters per second squared or more, it should not snap.